how to solve this, that we have to see in this session, today's session. So here you can see that if t is equal to 0, then the acceleration term that we are going to find out from this ordinary differential equation, that we can see that at t is equal to 0, we are getting the acceleration term is 0. That is, right hand side is equal to left hand side is equal to 0. So that we don't want. So for the at first step, that we have to find out what is the value of x displacement, that we have to find out at t is equal to 0. Here you can see that at acceleration, when we are putting the t is equal to 0, and at t is equal to 0, force is 0. So here you can see that the acceleration is at time t is equal to 0, acceleration that we are getting is 0. That we don't want. So this type of problem we have to solve using different method for the first step, that at the time of t is equal to 0. At that time t is equal to 0, we are solving this equation, and after that at t is equal to h, that is increment, that we are going to choose h is equal to 0.05. At that time we are going to solve in the similar manner that we have solved in the last class. So solving this problem at the t is equal to 0, first we will rearrange the acceleration term. That is, acceleration term that we are getting from the ordinary differential equation is x double dot is equal to 2f of t minus 16 pi square x. That this is our forcing this is our function, ordinary differential equation. This equation, then we are going to use the central difference method to solve this differential equation. This is our central difference method formula. Xi plus 1 is equal to 2xi minus xi minus 1 plus h square xi double dot. So here xi double dot, at ith iteration we know the xi double dot, that is acceleration. This is from our ordinary differential equation. So here we are going to put it here, and then we are going to solve by using central difference method. But at the t is equal to, at time t is equal to 0, at time t is equal to 0, that we have to assume the acceleration term. Okay, that acceleration term, assuming the amplitude from the 0, from the acceleration from the 0, this equation x double dot is equal to 0 plus alpha t. So I will solve this equation. Let's solve this x double dot is equal to 0 plus alpha t. So now this is acceleration term. Now if we are integrating, so then we will get velocity term, that is x double dot is equal to integration of alpha t dt. So we will get velocity alpha t square by 2. That is our velocity. Okay. This is no constant. No constant, because we are starting from 0 to t. So where we are starting from 0 to t, if there is a limit, then constant is. Okay. Again, so this is our velocity term. Okay. Now for the displacement, again we are integrating. So x dot dt t square by 2 dt. So again 0 to 2 t. So then what we are getting, x is equal to alpha So x is equal to alpha by 6 t cube. So then we are getting displacement term and velocity term. Okay. Now for the time step of h is equal to t, del t. So let's consider t at time step of h. Okay. So we can replace t with h. So then the acceleration for the next step will become what? It will become alpha into t. So t is here. What is t is our so for the next step x2 will come alpha into h. That is what? That is our time step. Okay. So that we are going to use for using. So what we are getting? Alpha is equal to x2 double dot by h. Okay. So we have the value of alpha. Okay. So this alpha we can put it here. Okay. So this from this what we are getting? We are getting the displacement at time step of h. Time step of h. Okay. So once we put it there, we will get alpha is by h t cube. Okay. So we have the displacement and acceleration relationship at a step of. So here h is t is what? T is our t already given that delta. So h is time step of t. Okay. So we can put it here h cube. So x2 become x2 double dot of 6 h square. So this is our relationship for displacement and acceleration. So now this equation we can put it in our this is our for the next acceleration that we are going to solve from our equation, that is this one. This is our next acceleration. What is that? This is our ordinary differential equation, that is from our given ordinary differential equation. So to now this at this point we have the acceleration term is not zero. Previously at t is equal to 0 the acceleration term is 0, getting 0, but at this time now we are not getting the t is equal acceleration term is 0. So suppose this is our equation 1 and the second equation is the acceleration equation that is from our ordinary differential equation. If we put x2 double dot, the value of x2 double dot to in this equation, this x2 double dot in this equation, so we can get the displacement equation. Okay. So now we have the displacement equation. This acceleration x2 double dot we can put it in this equation. So by rearranging we can get the value of x2 at the second step that we have for. Now the h is what? H is the time step. Okay, that time step for the second step, what will be the time step? That time step will be at h is equal to 0.05. What will be the value of forcing function? Force will be 25. At 0 is equal to 0, at at 0.1 is 50, so 0.05 will be the 25 Newton. So that 25 Newton we are going to put it in that equation. So we will get the value of x2. So we are getting the displacement at second step. Okay. Similarly, we can use this our central difference method formula for the next step of for the x3 and for the x3 and x4. So similarly, you have to use the same way to solve this for the displacement at other step value. Okay. So and for the speed, you have to use the speed for the x2. Speed that we have to use the our simple formula. X2 x2 dot is equal to x2 minus x1 divided by h plus h by 2 is the forcing function. This function is consist of three variable. X1, this is displacement. X2 dot, that is speed of and the time. So this is the function of all three. So from that, similarly we have to calculate for the x3 also using the same way. Now in the last class that we have discussed about the Ranjit-Gupta method. Today I will explain how the Ranjit-Gupta method will work, and after that we will see the Matlab code for that. Okay. So Ranjit-Gupta method is a computational method that gives the good accuracy. So in the Ranjit-Gupta method, the second order differential equation is reduced to the first order differential equation. So this is a damped force vibration equation. Here you can see that this damped force vibration. This is the second order differential equation. Okay, and this equation consists of displacement, velocity, and time. Now this equation that we have reduced to the two first order equations. Okay, first order. If we put let's say velocity x dot is a y. Okay, y, any other variable, that y. Okay, this is one equation. If we put y in this equation, x dot is equal to y. If we put x dot is equal to y in this equation, so what we are getting, y dot is equal to, yeah. So this is the function of what? So y dot is a function of what? Y dot is a function of x dot and t, and x dot is a function of y. So what we are done, the second order differential equation that we are reducing into two first order equation, x dot and y dot. Okay. So now in the Ranjit-Gupta method, what we are doing here, we are previously what we are doing, we are assuming the assuming for the displacement. Now in this Ranjit-Gupta method, we are going to assume for the velocity. So we are going to find out first velocity and then displacement. So Ranjit-Gupta method is a type of Taylor series expansion in the x and y. X is for our Taylor series expansion. For x, that is for displacement. Y that is our velocity. In this case, after this, that y we are considering as a velocity. Y is what? X dot means what? Velocity. Are you getting or not? Yes. Don't confuse. Just do one thing. In this equation, just consider, remember that x is our displacement, okay, and x dot is our velocity. So now that velocity, we are reducing that velocity into that x dot into y. So after that, y is our variable, which is velocity. Okay. So now y is our velocity and x is displacement. So after that, we are going to find out the y. Y is our velocity. Now we are going to find out the first velocity. After that, from the velocity, we are going to find out the displacement. So this is these are going, this we are going to do. So so this is a Taylor series expansion for the both x and y, for the for xi and yi, for the neighborhood of the x and y. So this is a simply a Taylor series expansion for the displacement. This is a Taylor series expansion for what? This is Taylor series expansion for velocity. So if we are going to replace but what is y? Yi dot what? That we are going to sorry, this is xi dot first one. Can see that. What is xi? X dot what? Y. So that we can replace the whole term as an average term. Okay. We are just replacing the remaining term as average. We can take the higher order terms as the average of this one. Velocity, and in this case, this is what? Acceleration. Yeah. So that again we are taking the average of this one. So this is our. So this is a slope, and we are going to ignore the higher order derivative. So average of this interval, average of all these slopes, that we can do in this form: 1/6 into dy by dt into at ti, at time of ti. I will explain how it is happening. Plus 4 of dy by dt I plus h by 2 plus dy by dt at ti plus h. Now, don't confuse with this equation. This is obtained by Simpson's rule. Suppose function sin x, okay, from for any time step of h, okay. So then we are dividing in two middle steps, first step, middle step, and last term at h, and this is at h by 2. So here what we are doing, first at I term, this is I plus what is I plus h by 2, and this is I plus h. Okay. So this is the time that we are going to find out at all three points, that we are going to find out the this average slope. That average slope is what? This is our acceleration. So I told this from this plot that we are dividing first I term h by 2 and h. Okay. So similarly, that we are going from this term. So this is for the Simpson's rule, but what is our aim? Aim is for the Ranju-Kutta method. So Ranju-Kutta method. For the Ranju-Kutta method, we are going to give the higher accuracy. The middle steps, we are divided into two steps. This middle step we are going to divide into two steps. This one, ti plus h by 2, ti plus h by 2. Okay. So first and last term is same like a Simpson's rule, but the middle steps that we are going to do in the two steps. So previously, what is the equation? The equation is h by 6 y1 plus 4 into y3 plus y4. But that 4 into y2 term we are going to replace with 2 into y2 plus 2 into y3. So the middle point, for that middle point that we are going to find out in this way. So So Ranju-Kutta method is same like a Simpson's rule, extension of Simpson's rule, but in this case we are getting the higher accuracy. So at at uh, at time t is equal to 0, suppose ti, what we are going to find out the displacement xi. Okay, and from this we have the initial condition. So we have the displacement and velocity for the initial condition at t is equal to, suppose t is equal to 0. So we have the xi, yi. So from that t1, x1 and x2, y1, we will get the function. This function is what? This function is our acceleration. So acceleration we will get. So now we have the at the first step, this step, we have the time. We already know displacement, velocity. Now the acceleration also. So now from this step we will get the first middle term. It at t2 is ti plus h by 2. Okay, then which is x2 is equal to that is our displacement. Is xi plus y1 into h by 2. Y that we are getting from the velocity. So for the velocity at first middle step, we are getting from acceleration for the first step. Then after that acceleration, we are getting the first middle step. So we will get the first middle, all the terms from the for the first middle step. So for the t3 at the second middle step, this which is the ti plus h by 2, initial time plus time span, half of time span. So x3 is equal to the displacement at second middle step is xi plus y2 into h by 2. Y2 is our velocity at first middle step, y2. So we will get, similarly we will get y3 and f3. Now the last term, which is t4 is equal to ti plus h at the last one. So that point again we are getting the displacement, velocity and acceleration. So now we have all the terms at the all three points. So now that we are putting in the this recurrence formula. So we are getting the for the displacement. Okay, for the displacement at this point, what xi plus 1. We have the xi displacement at this value, xi plus h by 6 into y1 plus 2 into y2 plus 2 into y3 plus y4. Okay, these are y1, y2, y3, y4. What is this? This is the velocity that we have calculated from Ranju-Kutta formula. Now yi plus 1. Yi plus 1 is 1. This is velocity. So yi plus h by 6 into f1 plus 2 into f2 plus 2 into f3 plus 2 into f4. f1, f2, f3, f4. What is this? This is the acceleration that we have calculated from Ranju-Kutta formula. So these are the four values divided, which is dx by dt from the divided by dx by dt and dy by dt. So these are the last time we discussed about these are the Ranju-Kutta formula method. From this formula we are going to calculate the displacement and velocity, and this displacement and velocity we are going to plot displacement versus time and velocity versus time in the Matlab. So till now, anyone have any problem? Got it or nothing? Anything? Okay. So after this, I will tell you the Matlab code. I already sent you the Matlab code for the simple problem. So for the Matlab, for the solving the ordinary differential equation, here we are going to use the ODE45. So in the Matlab, ODE45 is used to solve the Ranju-Kutta method to solve this ODE problem. So this is the syntax for the ODE45. So T solution, the time at different times that we are going to solve. Y solution, is the uh, the solution that we have to find out, which is our velocity or displacement that we have to find out. So ODE 45. So ODE 45, ODE function t span comma y0. So what is ODE function? ODE function is a function that handle to the ordinary differential that is to be solved. So this ODE function, from this ODE function we are going to solve the function that we are already already write in the Matlab, that ODE function that we are going to solve. T span is the time span over which the ODE needs to be solved. Y0 is the initial condition of the ordinary differential equation. T solution is the time values at which ODEs are solved, and Y solution is the matrix values which is corresponding to the time values in T. So at each time T. So the first problem we are going to solve for the two problems. One is the free vibration and another one is the forced vibration. So previously here you can see that the dy by dt is equal to function of time comma y. If the f of t comma y is equal to 0, then our problem becomes free vibration. So first we are going to solve for the free vibration. So this is a damped free vibration. So for this ODE function is mx double dot plus cx dot plus kx is equal to 0. Okay, so this is our second order ordinary differential equation. Now what we are going to do? We are going to second order differential equation split into two first order differential equation, that is velocity x1 is equal to x dot and displacement x2 is equal to x. Okay, so are you getting what we are done here? The second order differential equation that we are split into two first order differential equation, velocity and displacement. Okay, so the our ODE becomes, if we are changing put it x dot is equal to x1 in this first equation. So what we are going to get, mx1 dot plus cx1 plus of kx2, x2 is what, displacement, is equal to 0. So rearranging it, x1 dot is equal to minus c by m x1 minus k by m x2. So this is our velocity, and displacement is what, x2 dot is equal to x1. This is our displacement. So to solve these two equations, we need to do the simple numerical integration to solve to get the responses. So now we have the equation. Now we have to use the ODE 45 to solve to get the responses. So solving any Matlab, for the Matlab code, first we are going to define the global constants. After that, initial conditions. We already have the initial conditions, global constants, defining the function for solving the numerical integration for the first order, which is ODE 45. For the ODE 45, we have to define the function, and after that, we are going to obtain the time varying displacement. That we have to plot displacement versus time. So this is the code for the free vibration, responsible for the free vibration for the single degree of freedom system. So that I already told what is the ODE function that you have to get for the ODE 45. So this is our function for the velocity. Function is, let's define function dy is equal to test code to t comma y. So our velocity is the function of t and y. So dy is equal to that this is our function, that is our equation 2. Sorry, equation 3, sorry. This is equation 3. This velocity we are going to do for the ODE function, for the ODE 45. So this is our ODE function. Dy is equal to minus k of y2 divided by m minus c of y1. Y2 means that we already decided as y2 and y1. Okay, minus c of m. This y1 is our displacement. So now we already written the ODE function. That ODE function we need to call in the other Matlab code using the ODE 45. ODE 45. First of all, I will define all the constants: mass, spring constant, damping, and so from these three we can directly calculate the damping ratio, because we already have the mass, K and C. Already all three are given. So damping ratio we can directly calculate. C is equal to 2 under root of Km. So let's define the global constant. These three are global constant: mass, stiffness, and damping. Okay. So time step. Let's define the time step of 0.005. Okay. So total time is our 2 seconds. We are dividing 0 to time step of 0.05. So we will get the values at each time step: 0.05, 0.01, similarly up to 2 seconds. So these are the initial conditions. Y0 is equal to 0.05 and 0. So we have the velocity and displacement at initially. Okay, this one, and displacement at initially. This is the velocity. This is the displacement. Okay. So now we are going to use the for the ODE 45 T solution, Y solution, Y solution is equal to ODE 45. So in the bracket we have to write the this function name, test code 2. So this function we have written. So this is what? This is our times total time 0 to 2 in the time step of dt. Dt is what? 0.0005. This is our time span into y0. Y0 is the initial condition, velocity and displacement. Initial conditions are the 0.050. This is the for the velocity, and this is the for displacement. So we already given everything. So the Matlab code will solve these things. So now we have to plot displacement versus time. Okay. So T comma Y solution of 2. So of 2 means for the displacement. So we are going to solve for the displacement. So x level and y level are just x axis and y axis. X axis we are putting the time, and y axis is putting the displacement. Similarly, for the velocity, plot T comma Y solution 1. One is for what? One is our velocity, and second one is displacement. So the displacement we have already calculated for the second one, and the first one is for the velocity. So similarly, we are going to plot for the velocity versus time. So x level of time and y level is for velocity. So this is the code for the free vibration. So now I'm going to run this code. So this is the code that okay. So here you can see that velocity versus time plot, and displacement versus time plot. So similarly, we are getting all the values of in terms of matrix. So first term is what? First one is the velocity, and second displacement. So these are the at each time step 0, 0.005, 0.01. So each time step we are getting the velocity and displacement. So this is, you can see that at t is equal to 0, velocity is what we are given, 0.05. So this one, and displacement what we are given is 0. So in this way we are getting till time 2. So in this way we are getting the plot for the displacement versus time and velocity versus time. So you got how the things are happening in the ODE 45. Anyone have any problem? Okay, so try for the free vibration first. After that, I will tell you about the post vibration. Okay. Once you finish the free vibration, just tell me. Okay, for the post vibration. Hello everyone, please listen here for the post vibration. Okay, so in this case, post vibration, here we are getting the forcing function f of 0 sine omega t. So in this, so in the ordinary here OD, we are getting the mx double dot plus cx dot plus kx is equal to f0 sine omega t. Let's say here is f. So here is the forcing function is one extra term is coming in the post vibration. So so similarly we are going we are reducing this second order differential equation into two first order equation, that is the velocity and the displacement. Then the putting this velocity term in the equation 1 and displacement term in this equation 1, this OD becomes we are considering the forcing function as f. So this velocity term becomes this one and the displacement term is this one. So to solve this equation, we need to do the simple numerical integration to get the responses, that is displacement and velocity. So the similarly we have to define the global constant, defining the initial conditions, and defining the function for solving the numerical integration of the first order ODE, this first order ODE for the displacement, and after that we are going to obtain the quantities, displacement and velocity. And so this is the code for the post vibration response of the second simple degree of freedom system. So single degree of freedom system. So similarly we are defining the ODE function for the velocity. Here previously we have only one function. So we have to define the one ODE function, but in this case we have two functions, forcing function and the velocity function. So in this ODE function we are getting one more function, that is forcing function. F1 is equal to f sine 2 pi omega ft. So this is our force function and this one is our for the velocity. So now we are going to call this ODE function test code 3 in this main code for the solving displacement and velocity. So similarly we are defining the constant. After that force amplitude f we have to define is 5 here, and omega f that we have to define. These things we have to define. These quantities we have to define. After that our time step is 0.05 same, and total time is 0 to 3 seconds. So initial condition in this problem is velocity and displacement both are the 0 0. Initial velocity is 0, initial displacement is 0. So the T solution and Y solution, OD 45, test code 3, T, Y0. So now damping ratio that we have to calculate, and now we have to plot from the OD 45 we are getting the displacement and velocity. Now we have to plot displacement versus time. So plot T, Y solution 2. 2 is what? 2 is our for the displacement, and first one is for the velocity. So similarly we have to get the plot the T, Y solution of 1. So similarly we have to plot velocity versus time in this same way. In this code, anyone can say, can you tell me what is the problem in this line? Can anyone tell what is the problem in this line? Is it right or wrong? Y0, 0, 0. This line, is there any problem? Initial displacement. Is there any problem in y0 or is it correct? If I put 0, 0, is there any difference? Can you check? If I put y0 is equal to 0, 0, is there make any difference? Because in the plot value t comma y solution of 2 means y solution of 2 means what it is going to define is for the displacement t comma t is for the first column t and this one is for displacement. It is defined by column t comma y solution of 2. So t is for first column maybe 0, 0.005, 0.01, similarly 3 seconds. Similarly we are getting the displacement in this. So this is separated by comma. So this is the meaning of the comma, means you can't put directly without comma. If you miss this comma, then if there is a space, then the meaning will change. Just try with comma, without comma, what you are getting. But you can check in this here also. The column. There are 2 columns and 400 rows. Y0 also you can see. Y0 is initial only 1 row. If you put comma, then this will be 0.05 and this will 0. So take care of these things. So try for the first vibration and I will tell you the extra things.